So, for those of you who don't know me, my name is Rin Zenith. Not friend, but I am a friend. Anyway, and I am an elf from space who lives in my little camper shuttle, and I travel around and play video games and talk to people through stream and stuff, because it's nice, it's a nice way to spend time. I don't always look quite like this. This is my my pajamas, basically, because I just wanted to have a nice chill conversation with you as we talk about and learn about space together, because despite me traveling in space all the time, there's a lot I kind of just take for granted, because there's so much it's just there, and a lot of my ship and everything is automated, so I don't put a whole lot of thought into how things work and stuff. So I'd like to learn a little bit more about the universe with you, if that's okay. So, because I'm not an expert myself, this isn't going to be like a lecture or anything. But I have been studying a few things that I haven't been before, like a basic astronomy textbook from Earth. Because, despite, traveling in space and stuff, it's actually... Here's the immersion break. You know I'm human, right? You know I'm from Earth, right? Anyway, so we're going to be studying Earth's understanding of astronomy and how the universe works and all that stuff. So, and apparently how the universe works is it conspires against me to crap on my internet and make all of my frames go away and just crash everything. Sometimes. Now it's okay. Now that no one's watching, it's okay. Just like how scientific experiments go, sometimes the result changes whether or not it's observed. So, my streams run better when no one's watching. Boom! Ah. Let's continue to work. If I go over here? Yes. I go here? Yes! Yes! Haha! I defeated you, Streamlabs. Take that. Okay. Ooh. My goodness gracious. Alright, so basically what I want to do with these is, I've been trying to learn a little bit more myself, but while learning stuff, of course, how it always is, especially if you have like ADD or whatever, you'll start reading something and then be like, oh, I want to learn more about that, or that brings to mind this other thought that I want to check out and stuff. So this isn't as organized as I thought it would be, which I have no idea why I thought there was any chance in the world that I could be organized. Like, I would actually put together a presentation for this? Who do I think I am? But I at least figured we could, learn some news about space together. But what I've been reading to get my initial grasp of it is, so OpenStax, okay, it's a secret. Not really a secret, because you Google it and you Google intro to astronomy, and this is one of the first results. So you get open access to an astronomy textbook. It's, a couple of years old, so with the way science is, some things are probably already outdated, but it's got a lot of really interesting stuff. This little section right here is, observing the sky and the birth of astronomy, and, basically how astrology kind of was the foundation of the studying of the sky. which some scientists are annoyed that it took the name astrology, and the actual study of the science of the stars is stuck with astronomy. But it's all good. It's fine. Doesn't matter all that much. And I'm really excited to keep reading this and learning more about this. And you can see my name. That's my name. My last name. But yeah, that's me. I am the point, the last point between the Earth, or the planet, and space. Basically. So basically, the universe is old as fuck. We know that much, at least. I would assume most of us know that much, at least. And because of the way light works, the way it travels, we can, through, you know, through crazy powerful telescopes and shit, we can actually look to the oldest parts of the universe. And, like, you know, astronomers can see, like, some of the glow from the Big Bang itself. It's so, like, it's always so amazing to me how you can look up at the stars and look out at the stars and basically be looking back through time. That's just incredible. And on some level incomprehensible and annoying, because it's also like, well, I'll never know what that star actually looks like right now. Unless you know, have space travel abilities that let you technically go faster than the speed of light. Not that you can actually travel constantly. Basically wormholes. I don't understand the intricacies of it at the moment, which is part of why I'm doing this, to learn more. But if you have any questions or thoughts, things that are standing out to you, you know what? Let's make this easier on me, and just read some recent news from space, and that may get us understanding a little more, and at least understanding what questions we should be asking right now. So here's some recent news. This was posted today. It's from NASA's website. NASA's Roman and ESA's Euclid will team up to investigate dark energy. Okay, so I do know a little bit. So I don't know, this article probably, I don't know how much this article is going to go into it, but if you're not familiar with what dark energy is, neither are the rest of us. Is basically my understanding. You know how there's, you know, we can look out, we can see stars and sometimes planets, at least the planets in our own system. And we have understandings of principles of, like, gravity and such. Hang on, I have a better explanation written down. So the universe it looks empty, except for stars and the planets we can see, but it's mostly empty. To be honest, it's mostly empty. It's significantly, I don't remember the exact number. I think there's like, I don't know, I just read it. Let me see. Let's look together. I just read that. Oh, so the air we breathe on Earth has about 10 to the 19th power. That's a shit ton of atoms in each cubic centimeter. That's insane. That's so much. That's just the air we breathe. You know, it seems like there's nothing there, but there's so many atoms in just air. And we think of air as empty space. So in the So in the gas of the galaxy, there's about 1 atom in every cubic centimeter. In intergalactic space, the space between galaxies, is filled so sparsely that to find 1 atom on average, you must search through a cubic meter of space. So the universe is so empty in most places, but there are atoms there. There is, space between stars is, there's a sparse distribution of gas, mostly hydrogen, and mixed with tiny solid particles called interstellar dust. So, gas and dust. Also, my apartment is also full of gas and dust. Gross. Anyway, because there's so little, though, it is a vacuum because, so there's basically nothing. But there is enough dust and gas and just kind of, celestial smog to get in the way to make it difficult to see objects that are significantly far away. That's why, we have insanely powerful telescopes now, and a lot of the times, telescopes and cameras that, have, long exposure photographs, essentially, so they can take a lot of time to capture as much light as possible over a long amount of time so they can see something that otherwise we wouldn't be able to see. That's a lot of what, to my understanding currently, which we should actually look more into that as well, things like the Hubble telescope does, And I believe also the, there is that other telescope that also takes very good pictures of the universe, but, it's still Pride Month, so I'm not going to say the official name of the telescope, because fuck that guy. And NASA won't change the name, so there we go. Anyway. So, what was I was talking about dark matter. Because that's what this article we're about to read discusses. So dark matter isn't really, as far as we know, isn't really like dust or gas, because whatever it is, we can't directly observe it with our current means. So we don't really know what it's made of or how much of it exists, but we know it's there because we can observe the pull of its gravity that the pull its gravity exerts on what we can observe. So, and we do know that it's not only within the Milky Way, it exists outside of the Milky Way. So let's go ahead and read this article, and then we'll probably have more questions by the end of it. So this is a beautiful illustration. So gorgeous, though. From the NASA's Goddard Space Flight Center. It's been a long time since I've been to a space museum, actually. I would really love to go to one again. So a new space telescope named Euclid, an ESA, a European Space Agency mission with important contributions from NASA, is set to launch in July. Okay, so it's launching next month, to explore why the universe's expansion is speeding up. It's speeding up? Oh shit. Well, that's something we can explore, definitely. Scientists call the unknown cause of this cosmic acceleration dark energy. Oh. By May 2027, NASA's Nancy Grace Roman Space Telescope will join Euclid to explore this puzzle in ways that have never been possible before. 25 years after its discovery, the universe's accelerated expansion remains one of the most pressing mysteries in astrophysics, said Jason Rhodes, a senior research scientist at NASA's Jet Propulsion Laboratory in Southern California. Rhodes is a deputy project scientist for Roman and the U.S. science lead for Euclid. With these upcoming telescopes, we will measure dark energy in different ways and with far more precision than previously achievable, opening up a new era of exploration into this mystery. Oh, that's exciting as fuck. Holy shit. Scientists are unsure whether the universe's accelerated expansion is caused by an additional energy component or whether it signals that our understanding of gravity needs to be changed in some way. Astronomers will use Roman and Euclid to test both theories at the same time, and scientists expect both missions to uncover important information about the underlying workings of the universe. Euclid and Roman are both designed to study cosmic acceleration, but using different and complementary strategies. Both missions will make 3D maps of the universe to answer fundamental questions about the history and structure of the universe. Together, they will be much more powerful than either individually. You know, I love it when they work together. Hi! Welcome in, Maxwell. How are you doing today? See, where did I leave off? Aha! Euclid will observe a far larger area of the sky, approximately 15,000 square degrees, or about a third of the sky, in both infrared and optical wavelengths of light, but with less detail than Roman. It will peer back 10 billion years to when the universe was about 3 billion years old. I'm doing well. Doing well. Stream had a rough start, but we're here, just learning a bit more about space and what's going on in the universe. Detail in Roman. Okay, so that's what Euclid will do. Roman's largest core survey will be capable of probing the universe to a much greater depth and precision, but over a smaller area, about 2,000 square degrees, or 1/20th of the sky. Okay. Its infrared vision will unveil the cosmos when it was 2 billion years old, revealing a larger number of fainter galaxies. While Euclid will focus on cosmology exclusively, Roman will also survey nearby galaxies, find and investigate planets throughout our galaxy, study objects in the outskirts of our solar system, and much more. That's cool. So, dark energy hunt. So the universe has been expanding ever since its birth, a fact discovered by Belgian astronomer Georges Lemaitre. It's fine. In 1927, and Edwin Hubble in 1929. But scientists expected the gravity of the universe's matter to gradually slow that expansion. In the 1990s, by looking at a particular kind of supernova, scientists discovered that about 6 billion years ago, dark energy began ramping up its influence on the universe, and no one knows how or why. The fact that it's speeding up means our picture of the cosmos is missing something fundamental. Yeah. Okay. Roman and Euclid will provide separate streams of compelling new data to fill in gaps in our understanding. Honestly, space is almost easier in some ways to explore than the ocean. Because space we can, you know, it's... basically, we just look at it. You know? I mean, sure, there's, you know, some satellites and rovers and stuff that we can set out to, you know, also test biology and geology and things like that. But, you know, for the most part, we're basically looking through telescopes and cameras, and that alone gives us a shit ton of information. Like, an absolutely phenomenal amount of information. The equipment that we would need to explore the depths of the oceans, like, with the amount of pressure and everything down there, like, it's, like, that's nuts. Also, there's ghosts down there. The ocean's haunted. There's so much space that it's a little bit, that's never held any life in it. So it's a little more difficult to be haunted in every corner of space, you know? But But yeah, you know, it's definitely, it's very difficult to study the oceans, but they are fascinating. I have always had a little bit of a love for marine biology too. So first, Roman and Euclid will study the accumulation of matter using a technique called weak gravitational lensing. This light bending phenomenon occurs because anything with mass warps the fabric of spacetime. The bigger the mass, the greater the warp. Images of a distant source produced by light moving through these warps looks distorted too. When those nearer lensing objects are massive galaxies or galaxy clusters, background sources can appear smeared or form multiple images. Okay. It's crazy to me how, like, galaxies can form in clusters like that, though. Like, hang on, I had... Like, look at that! That's insane! Because, like, I know I'm on, like, this is a tangent, but also... it's all tangents. That's all we're doing here. So the teeming stars of the globular cluster NGC 6544 glisten in this image from the Hubble Space Telescope. This cluster of tightly bound stars lies more than 8,000 light years away from Earth and is, like all globular clusters, a densely populated region of tens of thousands of stars. This image combines data from 2 of Hubble's instruments, as well as 2 separate observations. Ooh. The first observation was designed to find a visible counterpart to the radio pulsar discovered in NGC 6544. A pulsar is the rapidly spinning remnant of a dead star, emitting twin beams of electromagnetic radiation like a vast astronomical lighthouse. That's cool. This pulsar rotates particularly quickly, and astronomers turn to Hubble to determine how this object evolved in this cluster. Second observation was contributed data to this image was also designed to find the visible counterparts of objects detected at other electromagnetic wavelengths. Instead of matching up sources to a pulsar, however, astronomers use Hubble to search for the counterparts of faint X-ray sources. Their observations could help explain how clusters like this one change over time. Ah. That's cool as hell. Back to this article. So less concentrated mass, like clumps of dark matter. Ooh, we can click a little thing and learn more. Can create more subtle effects. By studying these smaller distortions, Roman and Euclid will each create a 3D dark matter map. That will offer clues about cosmic acceleration because the gravitational attraction of dark matter, acting like a cosmic glue that holds together galaxies and galaxy clusters, counters the universe's expansion. Tallying up the universe's dark matter across cosmic time will help scientists better understand the push and pull feeding into cosmic acceleration. The 2 missions will also study the way galaxies cluster together in different cosmic eras. Scientists have detected a pattern in the way galaxies congregate from measurements of the nearby universe. For any galaxy today, we are about twice as likely to find another galaxy about 500 million light years away than a little nearer or farther. Interesting. I wonder if we'll actually get results of this within our lifetime. You know, the results and observations from these satellites. I mean, probably. Unless something happens. This distance has grown over time due to the expansion of space. By looking further out into the universe to earlier cosmic times, astronomers can study the preferred distance between galaxies in different eras. Seeing how it has changed will reveal the expansion history of the universe. Seeing how galaxy clustering varies over time will also enable an accurate test of gravity. This will help astronomers differentiate between an unknown energy component and various modified gravity theories as explanations for cosmic acceleration. Huh. Roman will conduct an additional survey to discover many distant type La supernovae, a special type of exploding star. These explosions peak at similar intrinsic brightness. Because of this, astronomers can determine how far away the supernovae are by simply observing how bright they appear. Astronomers will use Roman to study the light of these supernovae to find out how quickly they appear to be moving away from us. By comparing how fast they're receding at different distances, scientists will trace cosmic expansion over time. This helps us better understand whether and how dark energy has changed throughout the history of the universe. The two mission surveys will overlap, with Euclid likely observing the whole area Roman will scan. That means scientists will be able to use Roman's more sensitive and precise data to apply corrections to Euclid's and extend the corrections over Euclid's much larger area. Euclid's first look at the broad region of sky it will survey will inform the science, analysis, and survey approach to Roman's deeper dive, said, Mike Seifert? Project scientist for NASA for the NASA contribution to Euclid and NASA's Jet Propulsion Laboratory. Together, Euclid and Roman will add up to much more than the sum of their parts, said Yun Wang, a senior research scientist at Caltech IPAC in Pasadena, California, who has led galaxy clustering science groups for both Euclid and Roman. Combining their observations will give astronomers a better sense of what's actually going on in the universe. 3 NASA-supported science groups are contributing to the new Euclid mission. In addition to designing and fabricating Euclid's near-infrared spectrometer and photometer, NISP instrument sensor chip electronics, JPL led the procurement and delivery. Yeah. Okay, ooh, we can get more information about Euclid. Ooh. Euclid exploring the dark universe. ESA's Euclid mission is designed to explore the composition and evolution of the dark universe. Yep. Yep. Okay, so the launch period is next month. It's going to launch from Cape Canaveral in Florida. It's gonna be the SpaceX Falcon 9. I have mixed feelings about SpaceX. Destination is Sun-Earth Lagrange Point 2. 1.5 million kilometers from Earth. Okay. 2 instruments there to the sky, 10 billion light years, 3D map of the universe. Okay. Ooh, how we can watch it live. That'd be fun. Okay, so it will be broadcasting live, next month, as the Euclid Space Telescope, which will explore the dark universe, is targeted to launch on the SpaceX Falcon 9 rocket from Cape Canaveral in Florida. 11:11 local time. On Saturday, July 1st. Oh, July 1st. Oh my god, that's this Saturday. That's this Saturday! A backup launch date of Sunday is foreseen. Okay. Just how to watch the launch online. You can go to the ESA Web TV directly, or the ESA YouTube livestream. Follow the launch live. Okay. Here's the launch program. We're gonna go here. We're gonna go here. Gonna subscribe now. Turning my notifications on. Heck yes. Honestly, rocket launches are not the most exciting thing to watch. I mean, they should be. I should be more excited to watch them. Like, what the heck is wrong with me, honestly? That I'm like, it's just a rocket launch. It is still pretty cool to watch, though. Probably be cooler to watch live, like actually being at the place in Florida. Unless, we have another another SpaceX related incident where they don't have what was it? Like, they didn't have the proper, what was it? You know what? There was that yeah, like there was this back in April. Yeah, The SpaceX Starship explosion ignited 3.5-acre fire and sent debris thousands of feet. U.S. Fish and Wildlife Service says. Because wasn't it that, they didn't have proper, So yeah, I have mixed feelings about SpaceX. You know, on one hand, I'm glad there's more chances, more funding for space-related missions and stuff because of this. But Elon Musk is a piece of shit who takes too many shortcuts. So, anyway. Okay, so what is this one? Oh my gosh, this was from 2019. W first will add pieces to the dark matter puzzle. Wide Field Infrared Survey Telescope was officially renamed the Nancy Grace Roman Telescope. Nancy Grace Roman Space Telescope on May 20th, 2020. Okay. So yes, so this is the Roman telescope that they're talking about, which we've already read about. We can read a little more. Sure, why not? So the true nature of dark matter is one of the biggest mysteries in the universe. Scientists are trying to determine what exactly dark matter is made of, so they can detect it more directly, but our current understanding has so many gaps, it's difficult to know just what we're looking for. Roman's ability to survey wide swaths of the universe will help us figure out what dark matter could be made of by exploring the structure and distribution of both matter and dark matter across time, space, and time. Why is dark matter such a perplexing topic? Scientists first suspected its existence over 80 years ago when Swiss-American astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving so quickly they should have been flung away into space, yet they remained gravitationally bound to the cluster by unseen matter. Then, in the 1970s, American astronomer Vera Rubin discovered the same type of problem in individual spiral galaxies. Stars towards the edge of the galaxy move too fast to be held in by the galaxy's luminous matter. There must be much more matter than we can see in these galaxies to hold the stars in orbit. Ever since these discoveries, scientists have been trying to piece together the puzzle using sparse clues. There is currently a wide range of dark matter candidates. We don't have a very good idea of what the massive dark matter particles might be, which makes it difficult to work with how best to search for them. Roman's wide field surveys will provide a comprehensive look at the distribution of galaxies and galaxy clusters across the universe in the most detailed dark matter studies ever undertaken, thanks to dark matter's gravitational effects. These surveys will yield new insight into the fundamental nature of dark matter, which will enable scientists to hone their searching techniques. Most theories of the nature of dark matter particles suggest they almost never interacted with normal matter. Even if someone dropped a huge chunk of dark matter on your hand, you would probably perceive nothing. You wouldn't have any means of detecting its presence. All of your senses are moot when it comes to dark matter. You wouldn't even stop it from hurtling straight through your body and on towards Earth's core. This doesn't happen to regular matter, such as cats or people, because forces between the atoms in the ground and the atoms on our bodies prevent us from falling through Earth's surface, but dark matter behaves strangely. Dark matter is so inconspicuous it is even invisible to telescopes that observe the cosmos in forms of light our eyes can't see, from radio waves to high-energy gamma rays. Oh. Okay. So here's it going a little bit more into lensing, I think. If dark matter is invisible, how do we know it exists? While dark matter doesn't interact with normal matter in most cases, it does affect it gravitationally, which is how it was first discovered decades ago. So we can map its presence by looking at clusters of galaxies, the most massive structures in the universe. Light always travels in a straight line, but space-time, the fabric of the universe, is curved by concentrations of mass within it. So when light passes by a mass, its path curves as well, a straight line in a curved space. Light that would normally pass near a galaxy cluster instead bends toward and around it, producing intensified and sometimes multiple images of the background source. This process, called strong gravitational lensing, I still don't fully understand lensing, to be honest. I think we've read the same paragraph twice now. Strong gravitational lensing transforms galaxy clusters into colossal natural telescopes that give us a glimpse of distant cosmic objects that would normally be too faint to be visible. Since more matter leads to stronger lensing effects, gravitational lensing observations provide a way to determine the location and quantity of matter in galaxy clusters. Scientists have discovered that all of the visible matter we see in galaxy clusters isn't nearly enough to create the observed warping effects. Dark matter provides the surplus gravity. Scientists have confirmed earlier observations by measuring how much matter in the very early universe is normal and how much is dark using experiments like NASA's Wilkinson microwave and anisotropy probe. Even though normal matter makes up everything we can see, the universe must contain more than 5 times as much dark matter to fit the observations. Roman will build on previous dark matter studies by using so-called weak gravitational lensing. Okay. It tracks on how smaller clumps of dark matter warp the apparent shapes of more distant galaxies. Okay, and we read more about Roman's mission before. Okay. Oh, and this was last edited on June 12th. Okay. So let's see this. This one has a fun video, at least. So let's see. So, NASA's Roman Space Telescope to uncover echoes of the universe's creation. NASA's Nancy Grace Roman Space Telescope will detect vestiges of sound waves that once rippled through the primordial cosmic sea. That's a great string of words right there, though. Like, that sounds so sick. The primordial cosmic sea. According to new simulations, Roman's observations could extend these measurements into an unprobed epoch between the universe's infancy and the present day. Studying the echoes from this era will help us trace the evolution of the universe and solve pressing cosmic conundrums. Sound waves from the nascent universe, called baryon acoustic oscillations, BAOs, left their imprint on the cosmos by influencing galaxy distribution. Researchers have explored this imprint back to when the universe was 3 billion years old, or roughly 20% of its current age, 13.8 billion years. The same epoch Roman's BAO studies are optimized to investigate. Now a team of scientists has demonstrated that the mission could peer even farther back in time to explore impressions left by BAOs. This isn't something you can study in a lab, so we created mock universes and ran simulations, said Siddharth Satpathy, who led the study. I'm mispronouncing everything, I'm so sorry. Now a machine learning engineer at Cisco in San Francisco. He conducted the research while earning a doctorate in computational astrophysics from Carnegie Mellon University in Pittsburgh. We are excited to find that Roman will be powerful enough to study BAO remains in the universe's youth, he added. The team's findings were published September 11th in the monthly notices of the Royal Astronomical Society. So that's this little video there they made. This little animation that explains how BAOs arose in the early universe and how astronomers can study the faint imprint they made on the galaxy distribution to probe dark matter effects over time. In the beginning, the cosmos was filled with hot, dense fluid called plasma. Hot plasma soup, as it says down there. Excellent. I knew we were all soup. I knew that was all the universe is. It's just soup. Tiny variations In density, excited sound waves that rippled through the fluid. When the universe was about 300,000 years old, the waves froze where they were. Slightly more galaxies formed along the ripples. These frozen ripples stretched as the universe expanded, increasing the distance between galaxies. Astronomers can study this preferred distance between galaxies in different cosmic ages to understand the expansion history of the universe. Let's watch.
Immediately after the universe was born, it was too tiny and too hot for protons, electrons, and even photons to exist. Within a second, it had expanded and cooled enough for protons and neutrons, collectively called baryons, to form. Almost instantly, there was a rapid burst of sound waves triggered by tiny variations in this particle soup. Scientists call these waves baryon acoustic oscillations. The pressure waves traveled outward for 400,000 years until the universe thinned and cooled enough for light to travel through it. The universe became transparent, and the waves froze in place. Over time, the denser regions formed by the waves encouraged more star and galaxy formation than other areas. The imprint of those waves expanded with the universe, slowly accelerating due to dark energy. Today, with our snapshot of the universe, there is a slight tendency for galaxies to be separated from each other by a distance related to that expanding ring radius. Although difficult to see, it is detectable as a slight bump through careful surveys of many galaxies.
That is cool as fuck. Holy shit. Do we want to learn more about BAOs? Because, I mean, I do. Let's put that on the list. Holy shit. I would also like bao, as in dumplings. Those would be nice too. Definitely take some of those right now. Hot plasma soup. Hell yeah, baby. For most of its first 500,000 years, the universe looked extremely different than it does today. Instead of being speckled with stars and galaxies, the music back on, come on, get these vibes, come on. Instead of being speckled with stars and galaxies, the cosmos was filled with a sea of plasma, charged particles that formed a dense, almost uniform fluid. There were tiny fluctuations in about 1 part in 100,000, with a few variations. What few variations there were took the form of slightly denser kernels of matter, like a single ounce of cinnamon sprinkled into about 13,000 cups of cookie dough. I want cookie dough now, actually. Look up cookie recipes now? Goodness. No. Keep focused a little bit. Since the clumps had more mass, their gravity attracted additional material. It was so hot that particles couldn't stick together when they collided, they just bounced off each other. Alternating between the pull of gravity and this repelling effect created waves of pressure, sound, that propagated through the plasma. Over time, the universe cooled and particles combined to form neutral atoms. Because the particles stopped repelling each other, the waves ceased. Their traces, however, still linger etched on the cosmos. When atoms formed, the ripples essentially froze in place, carrying with them a bit more matter than the average across the universe. With the repulsive pressure of the plasma gone, gravity became the dominant force. Over the course of hundreds of years, clumps from the plasma that once filled the universe slurped up more material to become stars. Their mutual gravity pulled stars together into groups, ultimately forming the galaxies we see today, and slightly more galaxies formed along the ripples than elsewhere. While the waves no longer propagated, the frozen ripples stretched as the universe expanded, increasing the distance between galaxies. By looking at how galaxies are spread out in different cosmic epochs, we can explore how the universe has expanded over time. BAOs have left their mark on the cosmos, but we haven't fully examined their traces, said co-author Rupert Croft, a professor of physics at Carnegie Mellon University. By studying BAO impressions in an unprobed region, we can excavate cosmic fossils, which will allow us to unearth new information about the forces that have shaped the universe. Scientists have noticed a pattern in the way galaxies cluster together from measurements of the nearby universe. For any galaxy today, we are more likely to find another galaxy about 500 million light-years away than slightly nearer or farther. But looking out farther into space, into earlier cosmic times, mean that this distance, the vestige of the frozen BAO ripples, will decrease. Fascinating. So Roman will expand previous research by mapping the expansion of the universe to unprecedented detail. Yeah. Tapathy and his team showed that Roman surveys will be able to probe for BAO remnants 5 times farther than originally planned, back to when the universe was only about 600 million years old. That's crazy. I definitely want to try to keep up with this. Oh my goodness. Learning about the way the cosmos has expanded over time will allow scientists to explore dark energy, the mysterious pressure that is accelerating the expansion of the universe. Roman is optimized to survey the cosmos for BAO impressions across the middle of its current age because that's when scientists think dark energy transitioned from being a minor contributor to the contents of the universe to the most dominant force. But some theories hypothesize a bout of dark energy activity when the universe was much younger. Peering farther into the universe's past will help add pieces to the puzzle. We haven't extensively explored BAO imprints from when the universe was very young, because we need an enormous sample of galaxies to do so, said Jason Rhodes, a senior research scientist at NASA's Jet Propulsion Lab in Pasadena, California. That's where Roman comes in. Mission has such a wide field of view that observations like this will become possible. Roman's high-latitude spectroscopic survey will measure accurate distances and positions for millions of galaxies. Scientists plan to analyze how their distribution varies with distance by creating a 3D map of the universe, which will help us decipher how dark energy has shaped the cosmos over time. 2 additional Roman surveys will also study dark energy, and each technique will cross-check the others. The mission will provide important data to help scientists investigate and possibly even foresee the universe's fate. I am so psyched for this. Like I said, we probably won't, really hear anything about, or anything like super significant that we'll understand, that the layperson will understand, about these missions for several years, but I'm so excited. Oh my gosh. This is so cool. Ooh. How many pages is this? Oh, it's got sections and footnotes. How big is this article? Do I feel like reading this right now? Out loud? Oh no! No, I don't. That's a lot of pages. No thank you. I'm definitely interested in reading this later though. Or attempting to read it. Honestly, there's... Whoa, yeah. Yeah, I don't know how much of this article I'm actually even gonna understand, but I can try it later. Why not? Okay, so this video will help explain more how the Roman mission is going to use supernovae. Just let me pause the music again. And let's watch this, see if this helps me at least get a better understanding. So you might understand it better than I do.
How can astronomers determine distances in the far reaches of the universe? A small galaxy close in looks similar to a large galaxy farther out. This is a real challenge that researchers have found several solutions for. One method uses something called a standard candle. A standard candle is a type of object or event that emits a specific known amount of light, allowing scientists to find its distance with a straightforward formula. This works because light sources appeared predictably dimmer the farther they are from an observer. Since astronomers know how much light a standard candle gives off, they can determine its distance by measuring how dim it appears from Earth. Since only very bright objects or events are visible in the far reaches of the universe, the options for standard candles are limited. Some of the best and most reliable are exploding stars, called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. Some of the time, it may be a white dwarf and a larger host star. Scientists think the white dwarf steadily accumulates material shed by the host star, gaining mass in the process. When it reaches a specific tipping point, the white dwarf has gained enough mass to trigger a runaway reaction at its core, and it explodes spectacularly, sending out an expanding sphere of superhot material that glows from the energy of the explosion. In other cases, scientists think two white dwarf stars may form the binary. Either the stars finally merging together triggers the supernova, or it happens as they spiral in closer and closer, while the more massive of the two pulls material off its companion in the final few minutes. Before they merge, it reaches the same mass tipping point and goes supernova, always releasing a similar amount of energy. Because white dwarf explosions are all so similar, the energy and light output of type 1a supernovae are easy to standardize. Type 1a supernovae are rare in any one galaxy, occurring only once every 500 years or so in the Milky Way. But because there are so many galaxies, astronomers using current telescopes observe type 1a supernovae about 100 times a year. By comparing the observed brightness with the intrinsic brightness, astronomers can determine their distances within 6%. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will observe large patches of sky repeatedly, increasing the opportunities to spot these supernovae. Scientists predict Roman will see as many supernovae in 1 month as they've found in the last 20 years. Finding more of them will help astronomers refine the accuracy of this method, contribute to an improved three-dimensional map of the universe, and better understand how the universe has expanded and evolved throughout cosmic history.
Oh, some more about supernovae. It's bothering me. It should be novae, right? Unless would novae be the or is the narrator just mispronouncing it? I don't know. Let's put the music back on. Da-da-ba-ba. Many supernovae occur when massive stars run out of fuel, rapidly collapse under their own weight, and then explode because of strong shock waves that propel out from their interiors. These supernovae occur about once every 50 years in our Milky Way galaxy, but evidence shows that type Ia supernovae originate from some binary star systems that contain at least one white dwarf, a small hot core remnant of a sun-like star. Type Ia supernovae are much rarer, happening roughly once every 500 years in the Milky Way. I'll probably explain this in the video, right? I was paying attention. At least I was trying to. Okay, so in addition to providing a cross-check with the mission's other dark energy surveys, Roman's type Ia supernova observations could help astronomers examine another mystery. Discrepancies keep popping up in measurements of the Hubble constant, which describes how fast the universe is currently expanding. Predictions based on early universe data from about 380,000 years after the Big Bang indicate that the cosmos should currently expand at about 42 miles per second, or 67 kilometers per second, for every megaparsec of distance. A megaparsec is about 3.26 million light years. But measurements of the modern universe indicate faster expansion between roughly 43 to 47 miles per second per megaparsec. Roman will help by exploring different potential sources for these discrepancies. Some methods to determine how fast the universe is now expanding rely on type Ia supernovae. While these explosions are remarkably similar, which is why they're valuable tools for gauging distances, small variations do exist. Roman's intensive survey could improve their use of standard candles by helping us understand what causes the variations. The mission should reveal how the properties of Type Ia supernovae change with age, since it will view them across such a vast sweep of cosmic history. Roman will also spot these explosions in various locations in their host galaxies, which could offer clues to how a supernova's environment alters this explosion. Illuminating dark matter, we have read, for the most part, what exactly this telescope's mission is. Let's see. So April 25th, 2019. Mystery of universe's expansion rate widens with new Hubble data. Astronomers using NASA's Hubble Space Telescope say they have crossed an important threshold in revealing a discrepancy between two key techniques for measuring the universe's expansion rate. The recent study strengthens the case that new theories may be needed to explain the forces that have shaped the cosmos. I know this is going to be, like, fucking mind-blowing if this, changes our understanding of gravity. Like, goddamn. A brief recap. The universe is getting bigger every second. Space between galaxies is stretching like dough rising in the oven. But how fast is the universe expanding? As Hubble and other telescopes seek to answer this question, they have run into an intriguing difference between what scientists predict and what they observe. Hubble measurements suggest a faster expansion rate in the modern universe than expected, and based on how the universe appeared more than 13 billion years ago. These measurements of the early universe come from the European Space Agency's Planck satellite. This discrepancy has been identified in scientific papers over the last several years, but it has been unclear whether differences in measurement technique are to blame, or whether the difference could result from unlucky measurements. The latest Hubble data lower the possibility that the discrepancy is only a fluke to 1 in 100,000. That is a significant gain from an earlier estimate, less than a year ago, of a chance of 1 in 3,000. Yeah! Wow. These most precise Hubble measurements to date bolster the idea that new physics may be needed to explain the mismatch. Holy shit! The Hubble tension between the early and late universe may be the most exciting development in cosmology in decades, said lead researcher and Nobel laureate Adam Rees of SDSCL and Johns Hopkins University in Baltimore, Maryland. This mismatch has been growing and has now reached a point that it is really impossible to dismiss as a fluke. This disparity could not plausibly occur just by chance. Tightening the bolts on the cosmic distance ladder. Scientists use a cosmic distance ladder to determine how far away things are in the universe. This method depends on making accurate measurements of distances to nearby galaxies and then moving to galaxies farther and farther away, using their stars as milestone markers. Astronomers use these values, along with other measurements of the galaxy's light that reddens as it passes through a stretching universe, to calculate how fast the cosmos expands with time, a value known as the Hubble constant. Rees and his shoes, supernovae H0 for the equation of state team, have been on a quest since 2005 to refine those distance measurements with Hubble and fine-tune the Hubble constant. In this new study, astronomers used Hubble to observe 70 pulsating stars called Cepheid variables in the Large Magellanic Cloud. These observations helped the astronomers rebuild the distance ladder by improving the comparison between those Cephids, Lordy, and their more distant cousins in the galactic host of supernovas. Rees's team reduced the uncertainty in their Hubble constant value to 1.9% from an earlier estimate of 2.2%. Ooh, okay, so it's that. That. Look at that. Yeah, let me just get a whole look at that. Space is, it's difficult not to get overwhelmed, you know. This is a ground-based telescope's view of the Large Magellanic Cloud, a satellite galaxy of our Milky Way. It is much smaller than the Milky Way. The inset image, taken by the Hubble Space Telescope, reveals one of many star clusters scattered throughout the dwarf galaxy. The cluster members include a special class of pulsating star called Cepheid. Cepheid. Got it. Got it. These cluster members include a special class of pulsating star called a Cepheid variable, which brightens and dims at a predictable rate that corresponds to its intrinsic brightness. Once astronomers determine that value, they can measure the light from these stars to calculate an accurate distance to the galaxy. When the new Hubble observations were correlated with an independent distance measurement technique to the Large Magellanic Cloud, using straightforward trigonometry, the researchers were able to strengthen the foundation of the so-called cosmic distance ladder. This fine-tuning has significantly improved the accuracy of the rate at which the universe is expanding, called the Hubble constant. As the team's measurements have become more precise, their calculation of the Hubble constant has remained at odds with the expected value derived from observations of the early universe's expansion. Those measurements were made by Planck, which maps the cosmic microwave background, a relic afterglow from 380,000 years after the Big Bang. The measurements have been thoroughly vetted, so astronomers cannot currently dismiss the gaps between the two results as due to an error in any single measurement or method. Both values have been tested multiple ways. This is not just two experiments disagreeing, Reese explained. We are measuring something fundamentally different. One is a measurement of how fast the universe is expanding today as we see it. The other is a prediction based on the physics of the early universe and on measurements of how fast it ought to be expanding. If these values don't agree, there becomes a strong likelihood that we're missing something in the cosmological model that connects the two eras. So, new study. Astronomers have been using Cepheid variables as cosmic yardsticks to gauge nearby intergalactic distances for more than a century, but trying to harvest a bunch of these stars was so time-consuming as to be nearly unachievable. The team employed a clever new method called DASH, drift and shift. Nice. Using Hubble as a point-and-shoot camera to snap quick images of the extremely bright pulsating stars, which eliminates the time-consuming need for precise pointing. So 3 steps of the Hubble constant. There's Earth. There's Cepheids within the Large Magellanic Cloud. Okay. It's Hubble. Galaxies hosting Cepheids and Type Ia supernovas. Light redshifted, stretched by expansion of space. Distant galaxies in the expanding universe hosting Type Ia supernovas. This illustration shows the 3 basic steps astronomers use to calculate how fast the universe expands over time, a value called the Hubble constant. All the steps involve building a strong cosmic distance ladder, starting with yes. We read that. Ooh, PDF. Don't mind if I do. When Hubble uses precise pointing by locking onto guide stars, it can only observe one Cepheid. Cepheid? I already forgot it. For each 90-minute Hubble orbit around Earth. So it would be very costly for the telescope to observe each Cepheid. Explained team member Stefano Casertano, also of SDSCL and Johns Hopkins. Instead, we searched for groups of Cepheids close enough to each other so that we could move between them without recalibrating the telescope pointing. These Cepheids were so bright, we only need to observe them for 2 seconds. This technique is allowing us to observe a dozen Cepheids for the duration of 1 orbit. So we stay on gyroscope control and keep dashing around very fast. Nice. Okay. The Hubble astronomers then combine their results with another set of observations made by the Araucaria Project, a collaboration between astronomers from institutions in Chile, the US, and Europe. This group made distance measurements for the Large Magellanic Cloud by observing the dimming of light as one star passes in front of its partner in eclipsing binary star systems. The combined measurements helped the Schutz team refine the Cepheids' true brightness. With this more accurate result, the team could then tighten the bolts of the rest of the distance ladder that extends deeper into space. The new estimate for the Hubble constant is 74 kilometers, 46 miles per second per megaparsec. That means that for every 3.3 million light years further away a galaxy is from us, it appears to be moving 74 kilometers faster, or per second faster, as a result of the expansion of the universe. The number indicates that the universe is expanding at a 9% faster rate than the prediction of 67 kilometers per second per megaparsec, which comes from Planck's observation of the early universe, coupled with our present understanding of the universe. So what could explain this discrepancy? One explanation for the mismatch involves an unexpected appearance of dark energy in the young universe, which is thought to now comprise 70% of the universe's contents. Wow. Proposed by astronomers at Johns Hopkins, there's not an extra S in there, Ren. The theory is dubbed early dark energy and suggests that the universe evolved in a three-act play. Astronomers have already hypothesized that dark energy existed during the first seconds after the Big Bang and pushed matter throughout space, starting the initial expansion. Dark energy may also be the reason for the universe's accelerated expansion today. The new theory suggests that there was a third dark energy episode not long after the Big Bang, which expanded the universe faster than astronomers had predicted. The existence of this early dark energy could account for the tension between 2 Hubble constant values, Reese said. Another idea is that the universe contains a new subatomic particle that travels close to the speed of light. Such speedy particles are collectively called dark radiation, and include previously known particles like neutrinos, which are created in nuclear reactions and radioactive decays. Huh. Yet another attractive possibility is that dark matter, an invisible form of matter, not made up of protons, neutrons, and electrons, interacts more strongly with normal matter or radiation than previously assumed, but the true explanation is still a mystery. Reese doesn't have an answer to this vexing problem, but his team will continue to use Hubble to reduce the uncertainties in the Hubble constant. Their goal is to decrease the uncertainty to 1%, which should help astronomers identify the cause of the discrepancy. Okay, so what have we learned so far today? So they're launching a telescope this coming Saturday that's focused on observing the early universe and dark matter, and it's going to be using supernovae as lenses. Kind of. This is why I didn't do well in school. Part of why. But I might finally be getting that diagnosis next month. Anyway, and then 4 years from now they're launching another telescope that's going to assist in the research of Roman by looking at something more specifically, more closely. So that's exciting too. And we're doing this research because trying to figure out what dark energy is, how it works, and why the universe is expanding faster than expected. Because from what I'm understanding, it seems like the universe is... I mean, it, you know, again, it's hard to tell because looking at the universe where the Big Bang began from our perspective is, you know, that was 13 billion years ago. So that's old news. So it could have started slow and then it's been expanding. Yeah. Why is it getting faster? And what does dark energy have to do with it? Or what does dark matter have to do with it? Okay. Okay. So that's interesting. Very confusing still. But again, I'm still... I enjoy reading these articles, but I'm still, you know, pretty new to the study of astronomy, so... I'm fascinated though, and I'm definitely gonna try to remember to watch the launch this Saturday. Unless it gets postponed. Who knows? Could be raining. I think there are a couple of... It is cool. It is so cool. I think there are some tropical storms out in the Pacific though that they're keeping an eye on. So I'm really excited to keep up with this and learn more to actually understand it. What else do we have? So oh yeah, because I opened a whole bunch of tabs because that's how my brain works and fails to work. So let's start breaking it down, you know? Because I don't know how much more reading I can do right now. At least reading out loud. 101. Must see cosmic objects. Centaurus A. Centaurus A is a standout object in the southern hemisphere observers. It hasn't yet. Oh no. It hasn't crashed on me yet. That's only like, how you doing today, Glock, by the way? How'd y'all manage with we're doing like the mercenary runs in RE5 last night, right? It's fine. It's fine. I'll upgrade it someday when I have money. Anyway. But Centaurus A. What's Centaurus A like? It's a standout object for southern hemisphere observers. I am never on the southern hemisphere because why would I do that? It's often called the Hamburger Galaxy. Oh, fuck yeah. Because of the two regions of the stars, the bun that surround a dark, dusty lane, the burger, that... Yeah. That's great. I love it. I love it when there's just silly names for shit. There's like someone fucking... Right? Holy shit, like who fucking looks at this and then goes, you know what? It looks like a fucking hamburger. Let's name it the Hamburger Galaxy. Like, I love it. That's so dumb. It's amazing. Bless you, you crazy sons of bitches. It's a heck of a meal. A mere 12 million light years away, Centaurus A has a diameter of about 60,000 light years. It's fat too. It's a fat burger. It was a Scottish astronomer, James Dunlop, who discovered in GC 5128 in 1826 using a 9-inch reflecting telescope in his observatory in Parramatta, New South Wales. Astronomers gave the catalog name Centaurus A because it was the first radio source discovered in the constellation. Both Hamburger Galaxy, I'm not calling it its alphanumeric designation, it's the Hamburger Galaxy, baby! Both its appearance and its radio emission have their roots in galactic collision. The main body... Let's keep looking at it. The main body of Centaurus A giant elliptical galaxy, is absorbing a smaller spiral galaxy. Delicious. The two objects collided more than 200 million years ago, creating large regions of star formation. This collision also probably aided the growth of a supermassive black hole in the center of the galaxy. Current estimates of its mass put it in the range of about 55 million times that of the Sun. To find the Hamburger Galaxy, aim your telescope 4.5. I don't have a telescope. Why would I have a telescope? Why would I do that for? You think I need a telescope, honestly. I really should get a telescope. Someday, I'll have money and can buy a telescope. But to find it, if you have a telescope, aim your telescope 4.5 degrees due west of magnitude 3.5 mu Centauri. Also, again, it's in the southern hemisphere, so unless you're like in Australia or South America, get fucked. Well, no, that's a loss for us. We can't see the Hamburger Galaxy, Glock. That's a loss for us. Oh, you missed it earlier. There's That's okay. That's why I'm here, to read it all out loud and then horribly translate it. But here's the Bug Nebula, and it looks great. I love it. Amateur astronomers named the Bug Nebula, and they were right to name it that. Look at it. Behold. It's beautiful and perfect. Incredible. For its insect-like shape, but because the bug's apparent size is only 2 feet. 2 feet? That shape is only so... No. It's gorgeous. Beautiful color. Recent pictures taken with the Hubble Space Telescope have revealed much more detail. Now it's often called the Butterfly Nebula. Well, it's still a bug, okay? It's still an insect. Whatever name you give it. Bug Nebula is on a number of top 10 lists, no surprise, considering its visual magnitude of 10.1 makes it one of the brightest planetary nebulae known. It is also the most massive, and its central star has a surface temperature greater than, Jesus Christ, 450,000 degrees Fahrenheit, get fucked Celsius, making it one of the hottest stars in the universe. That central star, by the way, wasn't discovered until 2009. Astronomers didn't detect it because it's so hot that, just like me, most of its output is ultraviolet radiation, just like me, which the surrounding cloud of gas absorbs and then re-emits as visible light, just like me. The lack of visible light coming from the star, coupled with its bright surroundings, made spotting it difficult. It wasn't until... Hell yeah! Oh my god, star cake? Can you imagine? So that's what we should be doing, experimenting in space, you know? That's what we should be doing. Instead of like just, you know, sure, dark matter is cool and whatever, but we should be launching a satellite full of cake batter into these stars and making space cakes. Hell yes. Worth it though, for the sake of science. The lack of visible light coming from the star, coupled with its bright surroundings, made it spotting it difficult. Oh yeah, I guess so. I guess that would be it there. Delicious. Oh, we should probably research more on dark radiation, because they mentioned that in one of the articles. But now I'm just fascinated by the idea of radioactive space cake. Oh, if you observe the Bug Galaxy, Bug Nebula, that's what it's called, through an 8-inch telescope with an eyepiece that magnifies between 50 and 100 times, it looks like a galaxy that stretches east-west and is 4 times as long as it is wide. Powers above 150 times, you'll be able to see the 2 lobes on either side of the core. One on the western side is easiest to see, it has a tapered end. Faint arm to the east is more difficult catch. We're talking about, like, hamburgers and star cakes, like... Y'all, are we just hungry? Am I just hungry? Is that what's happening here? Star Cross. Southern Cross. With the possible exception of the Big Dipper, the Southern Cross ranks as the sky's most familiar asterism, a recognizable group of stars that is not a constellation. That's a new word for me. Shouldn't be, considering, but it is. Indeed. Its 3 brightest stars are among the 25 brightest in the whole sky. I lost where I was looking at for a second. The stellar pattern is so famous that 5 countries depict it on their flags: Australia, Brazil, New Zealand, Papua New Guinea, and Samoa. Mariners plying wait. This is a southern hemisphere bitch too. Get out of here. Unless, I don't know what hemisphere you're from, Maxwell, sorry. If you're from the southern hemisphere, then we can spend more time on the southern hemisphere objects, that's fine. Bernardsey has to be one of... That's wild looking. Ah, get wrecked, Australia! Bernard's E has to be one of amateur astronomers' all-time favorite binocular objects. This combination of 2 dark nebulae, Barnard 142 and 143, comes from American astronomer Edward Emerson Barnard's catalog of such objects. That's cool as hell. Fucking A. They get to be in winter. Fuck. It's so damn hot. Why is it so damn hot? We get heat warnings like every other day, and it's just like, no. Just let me die. I want to live in a freezer. It's the only way to survive. I mean, you would think being out in space all the time, I would be cold all the time. It's the cardigan. But yeah, nah. It's ridiculous how hot it is. Frickin' climate change, eh? The E lies against the rich Milky Way in Aquila. Starting at green hued. That's a lot of words that I don't want to... Okay. I guess this is mostly a guide to actually look at them, and I don't have a telescope or nothing. That's what it is. That's what it is, yeah. Ooh, Rosette Nebula. That's a pretty one. You can look at that. Look at that. That's nice. Ooh, what should we learn more about? Should we learn about nebulas? What is a nebula? Why is a nebula formed? How do nebulas work? Let's figure this out. How are nebulas formed? Nebulae. Yeah, because Latin. Yep. Okay. Sure. What is a nebula? Other than being Karen Gillan's character in Guardians of the Galaxy. Karen Gillan's hot as fuck. Holy shit. Been in love with her, like, since she started as Amy Pond. Like, wow. Space is big. Space is cool. Fuck yeah. The center's currently closed, but we're still passionate about science and space exploration. Well, I wanna go when it's open again then. In this series, we'll take a quick tour through a science or space topic and give you an overview with some cool pictures. Today's topic, all about nebula. Fuck yeah, let's go, baby! A nebula is an enormous cloud of dust and gas occupying the space between stars and acting as a nursery for new stars. Sick. Did you think there was any fucking way it wasn't? Come on now. Yeah, it was just a goofy, silly little show. I hate when it gets too serious, you know? Like, give me the cheesy effects. That's where shit's at, you know? Hell yeah, I wanna be a silly old dude. I'm gonna remake my model to just be a silly old dude. Remember when the doctor wasn't sexualized all the time? Do we? It's been a long time. Back in the William Hartnell days. Everyone was already sexualizing that old man. God, what was the first one I watched? I think the first one was, like my brother rented, like first he rented the 5 Doctors, and then the Key to Time. So those were the first arcs of New Who I watched. Or Old Who. Classic Who. Technically my first Doctor, I suppose, was all 5 at once. though it, came about in the Fifth Doctor's run. But, since Key to Time was the first solo Doctor series I watched, or I do kind of consider the Fourth Doctor to be my first Doctor. But then, consistently watching, it was Eccleston. So, what is a nebula? I mean, talking about Doctor Who, it still counts, like I said, it's also space-themed media, not just reading articles and ruining my voice reading articles. All space-themed media can be discussed, it's just chill. This is just whatever, But yeah, so a nebula is an enormous cloud of dust and gas occupying the space between stars and acting as a nursery for new stars. The roots of the word come from Latin nebula. Nice. Nebula comes from nebula. Excellent. Which means a mist, vapor, smog. No. Fog, smoke, exhalation. I combined two words together. Damn it, VC Face. Stop it. I'm doing my best. And by my best, I mean... fuck you. So nebulae are made up of dust, basic elements such as hydrogen and other ionized gases. They either form through clouds of cold interstellar gas and dust, or through the aftermath of a supernova. For example, in the Carina Nebula, hot young stars erode and sculpt the clouds into this fantasy landscape by sending out thick stellar winds and scorching ultraviolet radiation. Low-density regions of the nebula are shredded, just like me, baby, while the denser parts resist erosion and remain as thick pillars. In the dark, cold interiors of these columns, new stars continue to form. In the process of star formation, a disk around the protostar slowly accretes onto the star's surface. Part of the material is ejected along jets perpendicular. What is words you're saying? Accretion disk? You're gonna make me look up so many more things for this one thing than I thought I had to. What's going on? Hell yeah. Yeah. Look at this guy. Look at this guy with his hair. Why don't astronomers dress like this anymore? Astronomers should always dress like this guy. This is the peak of science fashion. As with most things in the heavens, many people can claim the title of discoverer of nebulae. The first mention of it may have been in 964 by Persian astronomer Abd al-Rahman al-Sufi. That's true, I guess, but at least the hair, Like, I know some of them still grow their hair out like that, but more of them should. Get some nice puffy sleeves. The little cravat? Is that a cravat? I don't know. Whatever it is with the little frilly collar he's got, But this guy, this Persian astronomer, wrote about the Andromeda Galaxy noticing a little cloud. Early Arabic and Chinese astronomers also noticed the creation of the Crab Nebula, crab, as a result of a supernova in 1054. It wasn't until the 17th century and advances in optics that nebulae became more observed. In 1610, Nicolas Claude Fabry de Piersque discovered the Orion Nebula, which was then observed in 1618 by Jean-Baptiste Cizat. The first detailed observations, though, waited for famous scientist Christian Huygens. Sure, in 1659. Don't make me try to pronounce that again. But this guy was also the first to come up with the standard formula for centripetal force, which he published in 1659. Big year for this guy. Some nebulae are bright enough to be seen with the naked eye. The Orion Nebula is one of these, located between the stars in the constellation of Orion's Sword. Maybe you could see it if the city lights weren't so damn bright. Can't see shit. Sometimes I look up at the sky and I'm like, oh, is it cloudy tonight? And then I sit there for a minute and I see one star and I'm like, oh no, there's no clouds. It's clear. Cool. Many others are visible through telescopes depending on how many stars are around them to illuminate the dust clouds that form the nebulae. However, it's often hard to differentiate between star clusters, galaxies, and nebulae due to their similar makeup. Some example. Look at this. Look at this shit. Through advanced space telescopes like the Spitzer and Hubble Space Telescopes, we have plenty of gorgeous imagery of nebulae. Most of these are formed through infrared and false color images, but they are all striking. These images depict a wide variety of nebulae available for scientists to study. All of them cover light years of distance in space. Some are wispy, some are well defined. All of them are worth your time, baby. Right? Holy shit. My shitty little brushwork in my backgrounds and stuff does not do this justice, you know? Wow. Space is so fucking cool. And terrifying. Now that thing looks like a fucking like sea monster or something, like rising up like I'm sure it's real, right? It's not real, it can't hurt you, don't worry. The pillars of creation. The big space dildos. There you go. Holy shit. Why do all these stars look green? What the fuck is that? What the fuck is that? This isn't real. What the fuck is this? It's like fucking... Oh my god, wait, is this the, No, this is a different one, I think. Oh, this was our bug from earlier. This is a whole ass island, for real. Crazy. I love how, like, some of these look like fucking mountains, you know? And just like floating islands and shit, like you said. That's an eyeball. That is terrifying. I don't enjoy this one. Nope. This is gonna appear in my nightmares. Holy shit. This face is so scary. I wish it wasn't real. Oh my god, for real. Another eyeball. Why are there so many eyeballs? Why are there so many eyeballs? I don't like it, Glog. I don't like it. I'm gonna stay planet side forever now. I'm not a space VTuber anymore. It's too scary out here. I didn't do it. No. Oh, this one's nice though. That's nice. This is the bug, I guess, from earlier. Yeah. That's nice. That's nice. That's kind of nice too. It's not as scary. That looks comforting, you know? That looks like a warm hug from space. That's fun. This looks like tissue, and that's kind of freaking me out. And I like it. This one? It does! Oh, yeah, with a tiny head. And like the, yeah! You're so right. Oh my god. Nebula Kingpin is real and can hurt you. It's like a... not almost an eyeball, not quite. Kind of looks like a bunch of jellyfish stacked on top of each other, you know? Or like a fetus. You know, like it's still being formed. Yeah, it will hurt you. Yes, exactly. Oh, this one's fucking cool. And gross. This looks so gross. Yeah, it looks like mold. I like it. Yeah. 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 Ah, this is just a disc. Little bit, yeah. Like when it spills out at the grilled cheese and so. Oh lord, this is mitosis, right? That's the one, right? This looks like something's trying to crawl out of this space here. You know, it's going that way. This looks like a wizard. Like this is a wizard head. And it's got like the white hair and it's like blowing in the wind, and he's got like this cloak like billowing around, you know? Right? It's not just me. This is now dubbed the Wizard Nebula. Thank you. NASA, just letting you know, this is the Wizard Nebula now. More eyeballs. No thank you. Stop staring at me, space. Stop it. I don't like it. You're judging me. Like, this is insane. Look at this. This exists? This kind of shit exists in the world? Like, what the fuck? We're so tiny, Glock. But that's okay. That's a person! That's a person walking towards me in the opening of Doctor Who. It's the Doctor Who tunnel. This one? It's a stretched out gnome? Oh, there. Oh, in the middle? Maybe so. Looks like a person in like a little coat to me and like their hands kind of out. But maybe. Lord. Space gnomes. There are so many stars. And the universe is expanding so fast. And for what? Is there any more things it wants me to see? Oh, yeah, we know these. Right? Yeah, these guys. These are also known as the Seven Sisters. Yes, my dumbass. Got that bed full of squishmallows. I actually don't... Do I? No, I don't actually have any squishmallows. I'm not really a big plushie kind of person. I like collecting mini Tsum Tsums, though not really anymore since they don't really make the good ones anymore. They're so small, and you can stack them, so it's... It was easy to justify. I can get a lot of plushies, but they're small, so it's okay. But yeah, my dumbass used to look at this shit up in the sky and be like, that is the Little Dipper, because it's the same shape. Or at least based on the stars I could see, it was the same shape. And every bitch was like, no. It's not the Little Dipper, you dumb son of a bitch. And I'm like, but it's the right shape. And they were like, no. You're stupid. And they were right. They were right. I still don't know how to find the Little Dipper and Big Dipper. I'm not good at stargazing. Oh, plushie's the size of a 4-year-old? That's where it's at, though. Ah, yeah, see? Like they say, under typical suburban skies, you might be able to count 5 or 6 stars set in the shape of a tiny dipper. Yeah. See? Nice. I've been rambling for a bit. I mean, I suppose I've been rambling most of the stream. But, yeah, no, that's fine. But I had fun learning more about space things. Reading a lot of articles that I partially understood. And I might just do it again. I'm gonna keep learning about space. Keep finding articles that I somewhat understand. We can try to learn things together. Google stuff. Talk about Doctor Who. Maybe even Mass Effect someday. All kinds of stuff. Yes, I did! It's super fun! It's a great time! It's so great out here in space and doesn't constantly terrify me. This is awful, uninhabitable form of pain and suffering happens to be the most beautiful thing you'll ever see. Could say the same thing about me! Oh, Christ. But yeah. This was fun. I think I'll definitely do this again sometime. Probably not, a regular weekly thing, but I think, you know, just a couple times a month would be nice. Just chill out, have our little drinky drinks, get cozy, and learn about the beautiful horror that is space. On that note, if you come across, you know, I follow NASA and stuff on a few different things, but like, you come across like other like weird space shit that you're like, oh, Rin might be interested in this, like totally send it my way, because hell yeah, I'm down to learn more shit. I'm gonna call it for today. I'm gonna head on out. Thank y'all again. Have a great rest of your day, or whatever.